is what, 14 or 15?
Yeah.
That's what 15, 12, 3. 25, 26, do Proverbs and stuff. That's a good one.
See the new iPhone 7?
So I did all of these.
30.
Did you see the
Yes,
new
sir.
iPhone
If
7?
you want like the others,
I'm not
if
sure
you have
how I feel
questions.
about the, next week.
Let me know.
Going to all-
But hey, listen, there might be some others in this list that are bad, so I'll keep looking and see if there's any bad ones. It's just a trick sheet. Up to old trick knowledge. Fresh on trade, that's all it is. Trick sheet. Can you pass these two back? You probably copied this from last summer.
Oh, yeah. Thank you.
That was the original copy.
You're welcome. You're welcome. You're welcome. This second sheet I'm passing out is just from 12-6. That's the last section we covered today. One of those pieces is actually from the book, but top row I included, so that's why I wanted to give you a copy of that. We'll get to that, later on today. I figure I'd just get that to you ahead of time, just so you had a copy of that. Haley's here. Austin's here. Chloe. Thanks, Jason. Clayton. Okay. Liz. Michael. That's two. William. Oh, I'm sorry, ready? William, that's it? And how about William Oaks? Awesome. Brittany Jackson. Thank you. Colin. Art's here. Maggie's here. Paul. Scott. Luke. Dan. Thanks, Dan. Brett. Brittany Wilbur. Thank you. And Allie. Nope. And, what's the name? Michael. Thanks, Michael. Perfect. Hey, good afternoon, everyone. So today we'll be doing section 12.4, 12.5, and 12.6. If you have any questions on the 12.1 and 12.3 material, it could be a textbook problem set question, or just a concept. Please feel free to end the class. I'll leave some time to go over that stuff with you. I'll do that every class, you know. So if you have questions, just wait till the end. I'll be able to go over that stuff. So 12.4 is titled the cross product. So I'll put that up here. 12.4, the cross product. Cross product. And it's the cross product of two vectors. And the cross product of two vectors is a vector. We'll find it. The dot product of two vectors was not a vector, was it?
Scalar.
Scalar. The dot product of two vectors was a scalar. The cross product of two vectors is a vector. All right, so this Irish mathematician is the guy, I think Hamilton, he invented this thing. But the easiest way to find it is through making a matrix and finding something called a determinant. So I'm going to do that. And I'll make up two vectors. Let's say I got the vector, vector A is, let's say 1, 4, 3. Let's say vector B is 0, -2, 1. And what we're going to find is vector A cross vector B. We'll find that. Well, what we can do is find something called a determinant of a matrix. So at the top, everyone, I'm just going to put down I, J, K at the top of the matrix. I'll put the vector A, all their components right underneath it. And then I'll put vector B's components underneath this. Now if you have knowledge of matrices, you've worked with matrices before, then you know what a determinant is, and you probably already know how to find it. But it's real easy to find a determinant of a matrix. So I'm going to put an equal sign here and leave these 3 slots open for our cross product. The cross product of two vectors, and we make that cross. Right? It's just like an X. It's a cross. The cross product of two vectors is a vector. So how do you do this? Well, when you're finding a determinant of a matrix, this is a matrix, to find this first component, well, you wipe out the first column. That's what we do. We actually cross it out. We don't look at it. And you go to this value right here. See that 4? And we do this times this minus this times this. So if I had like, I'm going to go to like an A, B, C, D. Every time you're going to do AD minus BC. Every time we do this. So you can always just say, all we're going to do is do A times D minus B times C. And that's the value we're going to put in this first slot. So I'm going to wipe this out. What's 4 times 1? Subtract -2 times 3. And for the first time, I should probably write that out, just so everyone sees that. What is 4 times 1 subtract -2 times 3? That's the value going right there. What do y'all get? 10. So it's always AD minus BC. This times this minus this times this. If you have an ABC. You know what? I'm going to go all the way down to the third component. I think I'll skip over the middle component for now. So for the first component, I'm going to find that I wiped out the first column, right? We're going to keep doing this. What about that third component? Wipe out the third column.
Ah.
Wipe out the third column. And that times that minus that times that. AD minus BC. And you could probably do it in your head. -2 is that product. 0 times 4 is 0. What's -2 minus 0? -2. So far, so good? Yeah, find a cross product. It's rather easy, but you'll notice something. It does take a little more thinking in math than a dot product. Dot product's fast. But you got to do this 3 times, so it's actually a little bit more comprehensive. Well, for this last one, I'm going to star this, because when it comes to finding a determinant of a matrix, we do the same thing, but we always change the sign of the second value. We'll always change the sign. We'll do the same thing, and I'll just change the sign of my result. If I get a positive, I'll make it negative. If I get a negative, I'll make it positive. I'm really just putting a -1 on it. And that's what we always do for the middle component. So, I'm going to wipe out this middle column. AD minus BC. Whatever I get from my result, I'm going to change the sign. Or rather, just put a negative on it. So 1 times 1 minus 3 times 0. All right. 1 times 1 minus 3 times 0 Well, what do we always do for this middle component? We multiply a -1 to it, right? We're gonna assign a negative value to this, changing the sign. What's the overall result? -1. That's the cross product. So I'm gonna write it really big here. A cross B is the vector. 10, -1, -2. And this is huge, everyone. This is very powerful. I know that's the definition of this vector, from that mathematician Hamilton, but this is what's huge. The cross product of two vectors is orthogonal to each vector. The cross product of A cross B, that cross product, is going to be orthogonal to vector A and orthogonal to vector B. When I say that word orthogonal, think perpendicular. All right. So if I took,
So you're saying like A and B are perpendicular to each other?
no, A and B are not perpendicular to each other unless that dot product was 0.
Okay.
We can check it real quick. It could be. Let's just check. Is A perpendicular to B? The dot product would have to be what? 0.
Okay. So
It isn't, is it?
No.
No, but this is always the case. Let's just say vector A and vector B must occupy some plane in space. I'll use my table. Vector A and vector B must be occupying some plane. Some plane somewhere in space. Well then, the cross product of those two vectors will always be perpendicular to the plane occupied by those two vectors.
Oh, the
Always.
cross product. Okay.
Yep, the cross product will always be perpendicular to that plane occupied by those two vectors. So it'll be perpendicular to this vector, it'll be perpendicular to this vector.
Okay.
Now let's show that. Oh, let's show that. You know what that would mean? Do you all agree? The dot product of this vector with this vector should be 0. That's what it means. And the dot product of this vector with this vector should be what? So let's check it. I'll be honest, I check this every time whenever I do a cross product. Because my eyes, I'm looking all over the place. Weren't we looking at all the different columns? So I'll try to rush it. I'll try to rush it, and sometimes I'm like, I want to make sure I didn't look at the wrong column. So let's try this. Everyone, what's the dot product of this with vector A? It should be 0. 10 times 1 plus -1 times 4 plus -2 times 3. Is that 0?
Yes.
Check. And then the other one. 10 times 0,
0.
0. Plus -1 times -2
Plus 2.
plus -2 times 1.
Yeah.
Is the dot product 0 in both cases? Then you're absolutely certain you did the cross product right. And I'll be honest, me as math, I always check it. And the reason I always check to make sure I did the problem right, because when I'm doing a cross product, you saw it, I'm going like this, and going this time, this, and this, and this. And I'm going here, and this, and this. I easily, I could start like just wandering with my thoughts. I mess something up, so I always check it.
Does cross product always have to be applied to 3-dimensional? Can it be on two?
Has to be 3-dimensional is a brilliant question. You go, well, what if it's a 2-dimensional vector? Well, if you got the I and J, then just make K a 0. Like if you're in a 2-dimensional plane. But it always has to be a 3-dimensional vector, the cross product. Wasn't true with dot product, was it?
No.
But with the cross product, it has to be 3-dimensional. And you go, well, what if I want to deal with something in the XY plane? Well, in the XY plane, Z is equal to what? 0. Just make them zeros. So it's cool, and this is huge. So this will always be perpendicular, right, to the two vectors. Now, we could do all the math, but a lot of you probably know about this. What if we did B cross A? Well, I would have put the B here, and then I put the A here, and I would know the math, but I bet you could predict the answer. You know what happened to all these? They would all be the opposite sides. Because that vector has to be what? Orthogonal to both of them, right? You can do all the math. You could go in there and do all the math, but you would find it would be the same answer, but all the signs would be what?
Reverse.
And so remember about my table? Remember I said, everyone, here's my two vectors. Occupying some plane. The cross product of the two vectors is orthogonal or perpendicular to that plane. Perpendicular to each vector. Then the other vector must be going in the total opposite what? Direction. So I'm going to take this and slip it underneath the table. That just means that's why they all got assigned negatives. Does that make sense? So
A cross B, B cross A, they're always gonna be reversed in terms of signs. Cool, but when you do A cross B, you always put the A vector here and the B vector there. So if they ask you to do, find U cross V, they want you to put U there and then V there. And after a while, everyone, you're gonna find it silly to keep writing these IJs and Ks. Do we need them? So you're probably not even gonna write these. You'll probably just do this and do the math. Cool. Awesome. All right. Hey, so that's a cross product of two vectors. But the cross product of two vectors will always be orthogonal to each vector. Well, here comes our next theorem. We'll prove some stuff today, but we're not going to prove this theorem. Again, it's one of those theorems that the proof's in the book. This one we won't prove, but this is the magnitude of a cross product. I'll erase this. Is equal to the magnitude of vector A times the magnitude of vector B times the sine of theta. In terms of formulas, in 12.4, there's not many. Formulas are theorems, but that's a huge one.
Oh, so this is not cos, this is sine.
I know, and everyone, I'm going to write that above this. We just did a theorem last class that looks like this, but it had a dot product. I want to write it because it helps you remember. Look, it was a dot product. It equals the magnitude of A times the magnitude of B times the cosine of theta. And yes, that angle theta, everyone, is the angle between the two vectors. If you want to add this, I won't write it on the board.